Hi, today we'll be introducing our work, Deep Shape from Polarization, where we re-examine the classical physics-based shape and polarization problem with a new perspective from physics-based deep learning. What is shape and polarization? SFP takes advantage of the fact that light reflected from an object becomes partially linearly polarized. The Fresnel equations relate this polarization to surface geometry. Why is it so difficult? SFP is an ill-posed inverse problem. In short, the same polarization image can correspond to multiple shapes due to ambiguities in the physics of polarization. Fresnel's equations govern how light interacts with surface material during reflection. They relate the energy of the parallel and perpendicular components of incident light to the angle of the reflecting surface geometry. From these equations, we find the golden equation of SFP, the transmitted radiance sinusoid, which relates the measured intensity of reflected light through a linearly polarized filter to the polarization angle of the filter. However, herein lies the first difficulty in solving SFP. For any given polarization angle and measured intensity, two different phase angles, separated by pi degrees, both satisfy the equation. Accordingly, there will be a binary ambiguity in any surface reconstruction utilizing this equation. For most surfaces, the intensity of the light reflected from an object's surface is a linear combination of the diffuse and the specular reflection components. Specular reflection occurs due to the smoothness of the surface, while diffuse reflection arises from the roughness and surface imperfections. Using the TRS, we can derive equations relating the degree of polarization to the azimuth and zenith angles of the surface normals at every pixel, with the aforementioned binary ambiguity. Unfortunately, though, there is another catch. Two different models arise from the two different modes of reflection, and without knowing a priori which model dominates at which pixel, it is difficult to know which model to choose without additional assumptions or simplifications. Clearly, due to the ambiguity problem and the multiple reflection models, using polarization to reconstruct surface normals is no easy feat. In attempts to overcome these issues, previous physics-based SFP methods have derived numerous heuristics and assumptions to help make the problem more tractable. While we recognize the value in these principled physics-based approaches and the clearly important relationship that these aforementioned equations define, there remains a large room for improvement in the reconstructions they produce in many situations. Accordingly, we fuse physics-based reconstructions into our deep learning pipeline and attempt to overcome the inherent ambiguities using the structure that exists in the data. We make several contributions to the SFP problem. We make the first attempt at using deep learning for SFP and propose a model design which utilizes the physics to learn reconstructions, yielding state-of-the-art results in comparison to purely physics-based methods. We also provide the first SFP dataset with polarization images and associated ground truth surface normals. Our dataset is the first of its kind for the polarization problem and contains a range of objects and conditions. For each object in our dataset, we use a structured light 3D scanner to obtain a 3D point cloud of the objects. We then place the objects in varied lighting conditions and obtain polarization images. The Lucid Vision polarization camera employs a Sony sensor with a polarizing photodiode to capture all four polarization images in a single shot. Each image captures light linearly polarized at an angle of 0, 45, 90, or 135 degrees, which can then be fed into our network. We manually register the images with a 3D point cloud to establish ground truth surface normals. Our dataset contains significant variation in both the object shapes, materials, and paints, as well as the conditions during capture. Specifically, we take our images under three different settings: indoor in a lab, outdoor on a sunny day, and outdoor on a cloudy day. We use a physics-based convolutional neural network to predict the shape. We incorporate the physics of polarization using Fresnel's equations to compute physical priors, aiding the learning process. Using a learning-based method allows us to overcome many of the failures of pure physics-based approaches, while we show that adding priors guides us to more desirable solutions than learning can achieve on its own. Whereas previous methods require stricter assumptions on capture setup and therefore exhibit notable qualitative and quantitative variation under different conditions, our learning-based method remains consistent even under indoor and outdoor settings. We also show that learning alone isn't sufficient to achieve our realistic results. Without the guiding priors, we see the appearance of what we call texture copy artifacts, where non-geometry related features in the input image are also apparent in the surface normal reconstructions. When feeding our network only polarization images, these artifacts appear more frequently and more pronounced. By adding priors, however, we guide our network to learn geometrically realistic reconstructions. In order to further quantify the effects of polarization physics on our network, we ablate all polarization information from the network. From these experiments, we quantitatively and qualitatively show that with polarization, we're able to achieve significant error reduction. Compared to other previous physics-based methods, we perform much better in both quantitative metrics and qualitative observation. We hope that this work paves the way for future exploration in combining physics and learning-based methods for the shape and polarization problem specifically, as well as the other computer vision problems with ill-posed physics.